So, last lecture we had started our discussion on diffusion and dispersion. I had explained that diffusion is the process by which mass, energy, momentum is transported due to molecular velocity fluctuations and convection is due to the fluid flow. The fluid flow can be separated out into a mean flow plus a fluctuating velocity, and transport due to the fluctuating velocity is called as dispersion. Diffusion is due to molecular velocity fluctuations. The molecular velocity fluctuations are what are called isotropic, right? That is, they have equal magnitudes in all directions at equilibrium, and because of that there is no preferred direction for flow due to the molecular velocity fluctuations. However, if there is a variation in concentration or temperature in any one particular direction, then there will be a transport in that direction from higher concentration to lower concentration due to the molecular velocity fluctuations, and that process is what is called diffusion. We had taken the simple example of two chambers filled with two different kinds of gases, which we had considered to be of equal molecular weight for simplicity, and we had looked at the process of diffusion if the barrier between these two chambers is removed. Okay. Initially you will have only one gas on one side and the other on the other side, but after some time molecules of the gas on top will diffuse below, molecules of the gas below will diffuse above, and the concentration starts to get equalized. Okay. And when there is a concentration variation across the surface, you have a flux across that surface. Flux is mass transported per unit area per unit time. Physically, the reason is as follows. At this interface, at the surface, you have a higher concentration above the surface and a lower concentration below the surface. At the surface itself, the concentration is uniquely specified. In a molecular description, the molecules that are traveling from above to below the surface, they travel on average approximately one mean free path, okay, above the surface in a gas, where the mean free path is the distance between successive collisions of a molecule. Okay. The molecules that are traveling upward travel approximately one mean free path from below the surface. The concentration at the location above the surface is higher than the concentration at the location below the surface, and because of that you have a net transport of molecules from above to below. We had estimated the flux. Okay. The number of molecules going from above to below, okay, is approximately the root mean square velocity. So, the flux across the surface is equal to the velocity perpendicular to the surface times the concentration. Velocity perpendicular to the surface can be estimated as some constant times the root mean square velocity, because the root mean square velocity is the velocity of the molecules. Okay. So, the flux of molecules going from above to below is approximately equal to some coefficient of order 1 times the root mean square velocity of the molecules. That is the velocity perpendicular to the surface times the concentration at a location that is approximately a mean free path above the surface, where b is some constant. Okay. It is not exactly one mean free path, but it is of the order of a mean free path above the surface, and the ratio of the distance, average distance from which the molecule travel, and the mean free path is this factor b, which is also an order 1 quantity. That is for the molecules traveling from above to below. Molecules traveling from below to above travel from approximately a mean free path below the surface. Okay. And therefore, the concentration difference, the difference in fluxes above, flux above minus flux below, which is the net flux in the plus z direction. That is the difference in concentration between locations below the mean free path and above the mean free path. If the mean free path is much smaller than the macroscopic scale, in this case the distance between the two chambers, if it is much smaller than the macroscopic scale, the variation in concentration scales as the difference in concentration divided by the distance. Okay. And therefore, the concentration at a location one mean free path above or below, you can expand in a series using a Taylor series expansion. Okay. And it is equal to the concentration at that location plus or minus b lambda times the concentration derivative at that location plus higher order terms. And I told you that the higher order terms can be neglected because they have higher orders of lambda by L. Okay. And if you just retain the first term alone, you get an expression for the flux which is proportional to dCA by dZ. It has a negative sign because there is flux from regions of higher concentration to regions of lower concentration, and it has a coefficient which is equal to some order 1 factors times the root mean square velocity times the mean free path. Okay. Therefore, the diffusion coefficient, okay, is equal to some order 1 factors times the mean free path times the root mean square velocity, okay, in a gas. It is the molecular velocity and the molecular length scale. For a gas, the molecular length scale is the mean free path, and for a the molecular velocity is the root mean square velocity of the molecules in the gas. So, you get Fick's law of diffusion to within a multiplicative order 1 constant. Okay. We had estimated last time the root mean square velocity from the equipartition of energy. Half m Vrms square is equal to 3 by 2 kT. Okay. And for hydrogen, for example, we found out that it is about 2000 meters per second for hydrogen gas and about 500 meters per second for oxygen. That is the velocity with which the molecules in a gas are moving. Okay. And it is comparable to the speed of sound. So, the other thing that we need to estimate is the mean free path in a gas. Okay. And I will do this only for hard sphere molecules. Okay. As I said, the discussion here is restricted to what are called hard sphere molecules. Real molecules are more complicated, and you will need to modify the estimates a little bit for those real molecules that we will not discuss here. So, a hard sphere molecule has molecular diameter dm and it has a molecular velocity. Okay. Now, in a gas, this molecule as it travels in a gas, okay, it encounters other molecules. Okay. Okay. And then it encounters maybe another molecule at some other location. Okay. And this distance, okay, average distance between successive collisions is what is called the mean free path lambda. Okay. So, how is the mean free path related to the diameter of a molecule and the number density of molecules, the number of molecules per unit volume. Okay. So, when a molecule travels in a gas, okay, it traces out a cylinder. Okay. It traces out a cylinder of radius is equal to the diameter of the molecule, which is equal to the diameter of the molecule, in such a way that when the center of another molecule comes on this cylinder, okay, in such a way that when the center of another molecule comes on the cylinder, that means that the surfaces of the two molecules are in touch. Okay. In such a way that when the center of a second molecule comes onto the surface, the surfaces of the two molecules are in touch and there is a collision. Okay. So, it traces out a cylinder whose radius is equal to the diameter of the molecule, okay, in such a way that when some other molecule has center on the cylinder, that means that the distance between the two centers is equal to 1 diameter. That means that the surfaces are in contact. Okay. So, this has radius equal to the diameter of the molecule, okay, and it has certain length L. Okay. And therefore, this traces out a volume. The volume of the cylinder is equal to pi r square. Okay. The radius of the cylinder is equal to the diameter of the molecule, okay, times L. Okay. That is the volume it traces out as it goes. Okay. And with time, if it does not collide with another molecule, this the length of the cylinder will keep increasing. Okay. If the number density of the gas the number density is the number of molecules per unit volume. Okay. If the number density of the gas is n, right, then the number of second molecules in the cylinder, okay, the number of second molecules in the cylinder is going to be equal to the number density times the volume, okay, which is n into pi dm square L. Okay. That is the number of the second molecules in the cylinder. Okay. If the cylinder length is very small, then the number of second molecules is very small. As the length increases, the number of the probability of finding a second molecule in the cylinder increases with length. Okay. And you would expect a collision to take place when the number of second molecules is approximately 1. Okay. So that you have approximately 1 second molecule in that cylinder, so that the two molecules collide. Okay. So, the length is the mean free path when the number of second molecules is of the order of 1. Okay. So, the length is the mean free path when n pi dm square L is approximately equal to 1. So, okay, the length is the mean free path when the number of second molecules is approximately equal to 1. Okay. Therefore, the mean free path has to be equal to 1 is approximately equal to and you can easily verify that the right side has dimensions of 1 over length. N is number per unit volume and d square is length square. So, the right hand side will have dimensions of length. Okay. So, this is an approximate expression. You can do a more exact calculation in kinetic theory of gases, which I will not go into, and the exact expression is 1 by root 2 pi n times the molecular diameter square. So, that is the estimate of the mean free path, okay, the distance between collisions of a molecule. Okay. Let us estimate the mean free path for some simple gases. Okay. Estimate for hydrogen gas. Okay. Hydrogen gas, the molecular diameter, okay, is 2.6 angstroms. Okay. Nitrogen gas, sorry, let me first take oxygen. Yeah. Is equal to 3.7 angstroms, and nitrogen molecular diameter is equal to 3.8 angstroms. Okay. So, let us estimate the molecular diameters for these gases, for the mean free path for these gases having these molecular diameters. Okay. The number density, okay, number per unit volume, okay, from kinetic theory of gases, okay, P by kBT. Okay. The number of moles per unit volume is P by RT. number of molecules per unit volume is P by kBT, okay, where kB is the Boltzmann constant and R is the ideal gas constant. Since for the mean free path we require the number of molecules per unit volume, we have to use the Boltzmann constant here. Okay, let us estimate it at standard temperature and pressure. Pressure is approximately 1 atmosphere, 1.013 Pascal. Temperature, I will take it as 300 Kelvin. Okay. And the Boltzmann constant is 1.38 to 10 power joules per Kelvin into 300 Kelvin. Okay. And you can do this calculation to get 2.45 into 10 power 25 per meters per minus 3. Okay. That is molecules per meter cubed. Okay. 2.45 into 10 power 25 molecules per meter cubed is the number of molecules per unit volume. This number of molecules per unit volume does not depend upon the molecular weight, okay, or the molecular diameter. Okay. So, this is it depends only on the pressure and temperature. Okay. So, there is the number density. Okay. Now, using this we can calculate the mean free path. Okay. So, for hydrogen for example, okay, this is equal to 1 by root 2 pi n into 2.6 into 10 power minus 10 square, 2.6 angstroms, that is 2.6 into 10 power minus 10 meters, okay. 2.6 into 10 power minus 10 meters, okay, whole square. Okay. You can see that n has dimensions of meter power minus 3, so the mean free path will come out to be having dimensions of meters. Okay. And you can just substitute the value of the number density here and you will get the value as 1.4 into 10 power minus 7 meters. Okay. 1.4 into 10 power minus 7 meters is about 0.1 microns, okay, 1/10 of a micron. Okay. So, that is the mean free path in hydrogen, okay, gas. Okay. The mean free path for oxygen is into the diameter of oxygen, which is 3.7 into 10 power minus 10 meters, the whole square. Okay. And if you just substitute the value of n here, you will get 6.7 into 10 power minus 8 meters. Okay. This is also approximately 0.06 microns. Okay. It is a little less than 1/10 of a micron. Okay. That is the mean free path in oxygen. Okay. And the mean free path for nitrogen is equal to 1 by root 2 pi n into 3.8 into 10 power minus 10 whole square is equal to 6.4 into 10 power minus 8 meters. Okay. So, this is the molecular length scale, this is the microscopic length scale in gases. If you recall, I had said earlier that continuum approximation is valid when this microscopic length scale is much smaller than the system size. So, therefore, for hydrogen for example, the room temperature, the system size has to be much larger than 1.4 into 10 power minus 7 meters, and in oxygen and hydrogen it has to be much greater than about 6.7 into 10 power minus 8 meters. That is when the continuum approximation is valid. This length scale is still much larger than the molecular diameter. Okay. If I take lambda of H2 by the diameter of H2, okay, which is 1.4 into 10 power minus 7 by 2.6 into 10 power minus 10, both in meters. Okay. This turns out to be about 5.2 into 10 power 2. Okay. So, the ratio of the mean free path and the molecular diameter for hydrogen is about 500. Okay. So, the a hydrogen molecule travels 500 times its diameter before it collides with another molecule. Okay. And that for oxygen and nitrogen are greater than 100 or so. Okay. 6.7 into 10 power minus 8 by this is 1.8 into 10 power minus into 10 power 2. It is about 180, it is more than 100, and lambda n2 by d n2 is equal to 6.4 into 10 power minus 8 . This is approximately 1.7 into 10 power 2. Okay. So, a molecule typically travels 100 to 500 times its diameter between successive collisions at room temperature and at standard pressure. Okay. So, that is approximately the magnitude of the distance travelled. Okay. Now that we have these two estimates, we can then estimate what is the diffusion coefficient. Okay. D is equal to 2 AJ B VRMS into lambda. Okay. Okay. So, within a multiplicative constant, okay, it is equal to VRMS into lambda. Okay. For hydrogen, you can see that lambda is equal to 1.4 into 10 power minus 7, and the the speed was about 2000. Okay. So, this will be 2.8 into 10 power minus 4 meter square per second. Okay. I should put the units here. Okay. And this is for hydrogen. Okay. Okay, for oxygen, okay, is equal to about 6.7 into 10 power minus 8 into about 500 meters per second. Okay. So, this thing will be approximately 3.35 into 10 power minus 5, okay, meter square per second. Okay. Okay. So, this is the estimate for the diffusion coefficient of mass diffusion coefficient in gases. It is approximately 10 power minus 5 meters square per second in gases such as nitrogen, oxygen or air. It goes up to 10 power minus 4 in a small molecule gas like hydrogen or a small molecule gas like helium. Okay. So, in all gases these diffusion coefficients will have values that are approximately 10 power minus 5 meters square per second. Okay. That is the estimate for gases. Now, this was only an approximate calculation. In kinetic theory of gases, you can get a more exact estimate for the diffusion coefficient, the binary diffusion coefficient. Okay. This DAB, the binary diffusion coefficient, is the diffusion coefficient for molecule A, say, in a mixture containing molecules A and B. Okay. Okay. You can get a more exact expression for the binary diffusion coefficient of A molecules in a mixture of molecules A and B, say. Okay. And this is equal to 3 by 8 n DAB square into root of KB T MA plus MB by 2 pi MA where n is the number density dAb is the average diameter dA plus dB by 2 of the two molecules, okay, and Ma, Mb are the molecular masses. Okay. So, if you know the masses of both molecules that are diffusing, the diameters, the hard sphere diameters of both molecules that are diffusing, and the number density, you can actually get an estimate for the diffusion coefficient. And let us examine this estimate for the diffusion of water vapor. Okay. Let us say the mass of water is equal to 0.018 kg, okay, by Avogadro number. But I will come back to the mass, I will just put the diameter. The diameter of water molecules is 2.6 angstroms in air, okay, molecular weight 29, and diameter is equal to 3.7 angstroms, that of nitrogen. Okay. So, for this particular case, the number density at room temperature and pressure we had just calculated, okay, that is equal to 2.45 into 10 power 25 number molecules per meter cubed. Okay. dAb is equal to 2.6 into 10 power minus 10 plus 3.7 into 10 power minus 10 whole by 2 in meters, which is equal to 3.15 into 10 power minus 10 meters. 1 angstrom is 10 power minus 10 meters. Okay. The molecular weight m of A, okay, that is of water, okay, is going to be equal to, molecular weight is 18 into 10 power minus 3 kg by 6.023 into 10 power 23. This is 2.99 into 10 power minus 26 kg, and the molecular weight of air, if we take the molecular weight of air as approximately 29, okay, between 28 and 32 for nitrogen and oxygen, okay, it is 29 to 10 power minus 3 kg by 6.023 into 10 power 23, okay, which is equal to 4.82 into 10 power minus 26 kg. Okay. These are all substituted into the expression for the diffusion coefficient. Okay. dAb is equal to 3 by 8, okay, to the number density meters per minus 3 is the dimension of the number density, number per meter cubed. So, meters per minus 3 into dAb square, which is 3.15 into 10 power minus 10 meters the whole square, into kBt, that is 1.38 into 10 power minus 23 joules per Kelvin, into T is 300 Kelvin, into Ma plus Mb. Okay. If you add up this Ma plus Mb, you will get approximately 7.8 into 10 power minus 26 kg. Okay. divided by 2 pi into ma into mb. Okay, 2.99 into 10 power minus 26 kg and 4.82 into 10 power minus 26 kg. Okay. This whole thing to the half power. Okay. Okay. Whole thing under square root. Okay. And you can do that calculation and you will get the final result as 2.9 into 10 power minus 5 okay, meter square per second. Okay, 2.9 into 10 power 5 meter square per second. It was close to the 3 into 10 power minus 5 we had calculated earlier for oxygen. Okay. So, this is a more exact calculation with the prefactors in it. Okay. And the experimental results d is equal to, it is usually reported as 2.6 to 2.8 meter square per second, okay, in the range of 2.6 to 2.8 meter square per second. So, this simple calculation of the diffusion coefficient from the molecular properties has given us a very good approximation for the diffusion coefficient in gases. Okay. So, this completes my discussion on diffusion in gases. I started off with a molecular description and showed how the diffusion coefficient is related, that is the diffusion coefficient in Fick's law is related to the molecular properties, the root mean square velocity and the mean free path, and how the mean free path is related to the number density of molecules, the molecular diameter. On that basis, we had estimated the diffusion coefficient and had given you a more exact relationship for the diffusion coefficient for a binary gas mixture in this case, and showed that it is close to what you would expect, what you get, the result that you get from experiments. I will continue in the next lecture diffusion in liquids. Okay, there the estimates will be much more approximate before we go on to transport of momentum and transport of energy. I will continue this in the next lecture. Thank you.